All right. Once again, sorry to be late with a video here. I'll be honest, I was a little bit apprehensive to try out my new little stylus pen here. I'm going to have to figure out something long term in terms of how to make these videos a little bit better. I'm not going to be able to do the slideshow version, so it's not going to look nice like this. I'm going to be stuck in this mode. You'll see why in a couple of minutes. Let's go ahead and dive in though, okay? So this is over 6.4 heat capacity and calorimetry, some heat transfer problems. I'm going to go through the notes and I'm going to go through the example problems in this video. So it's going to be a long one. If you are looking specifically for the example problems, then you could probably skip about halfway through the video before I get to that, okay? All right, so first thing in the notes here, the concept of heat capacity. Usually heat capacity is given this variable C, okay? And I never see this C sub P. I always just see like capital C. It can be in terms of grams or in terms of moles. I'll talk about that a little bit later. But let's talk about what this actually means. So heat capacity is the ability or capacity of a substance to withstand temperature change when energy is added or removed from the substance or from the system. The units really tell the story, okay? So let me attempt to use my fancy little pen here. Okay, so heat capacity has units of joules per gram degrees Celsius. Okay, what does that mean? Well, I think the best way to talk about it is to talk about water. Okay, so water has a heat capacity of 4.18 joules per gram degrees Celsius. What does that mean? It means that for water, liquid water, I should say, for liquid water, it takes 4.18 joules of energy to heat or to raise 1 gram of water by 1 degree Celsius. It's almost as if there are like implicit ones here in the denominator. Okay? So it takes 4.18 joules of energy to heat 1 gram of water by 1 degree Celsius. Okay? So it's a measure of how much energy it takes to heat up 1 gram of a substance by 1 degree Celsius. Different substances have different values here, okay? And this could be in terms of 1 mole of the substance, okay? Or it can be in terms of 1 gram. Now, water is particularly interesting because it has a very high heat capacity. It's got among, I'm sure it's not the highest of all substances, but it's got a very high heat capacity of common substances. And the reason is water has very, very strong intermolecular forces, hydrogen bonds, right? Think about what it means to heat up a substance. If you think about it at the particle level. Temperature, let me go ahead and get my stylus ready again. Okay, temperature is proportional to the kinetic energy of the molecules or of the particles, okay? Which is equal to 1/2 mv squared, okay? So in other words, temperature is proportional to velocity of the particles, okay? So if the particles are moving faster, they're going to be at a higher temperature than if they were moving slower. Then that would mean that they were at a lower temperature, okay? Water molecules are good at resisting change in their velocity because they're very strongly attracted to each other through the hydrogen bonds, through the intermolecular force, okay? Another substance, say a nonpolar substance, something like methane, tetrahedral, nonpolar bonds, asymmetric structure, not very attracted to its neighbors. Methane would have a low heat capacity, Okay? Water has a high heat capacity. It's very strongly attracted to its neighbors. It's difficult. It takes a lot of energy to get those water molecules to change their velocity and to really increase in velocity. They like being with each other. Okay? That's called cohesion, right? Water is very sticky with itself. Okay? Hard to get it to move. So, let's talk about what that means, right? It means that water things that have high intermolecular forces, I should say, tend to have high heat capacities. There are other substances that would have high heat capacities. For example, an ionic solid. So if you consider what an ionic solid looks like, I feel like we've drawn this picture several times in the last couple of days. Ionic solids are made of alternating positive and negatively charged particles, cations and anions. These are strongly attracted to one another. It takes a lot of energy to get these to move, right? We know that these particles have, or that these substances have high melting points and high boiling points for the same reason, okay? It takes a lot of energy to get these particles to start moving, okay? So that's heat capacity. It is very much related to intermolecular forces in the same way that melting point and boiling point are related to intermolecular forces. Now, other substances do not have very high heat capacities. Metals, for example, have relatively low heat capacities. We can talk about why for just a minute. If you consider what a metal substance looks like at the particle scale, we typically represent metals as being metal ions that are floating in a sea of electrons, sort of delocalized electrons. So that's kind of a messy looking drawing there, but if you consider it, the negative charges there are just delocalized electrons that are sort of, they have mobility. So, for example, a metal is very good at conducting electricity due to the mobility of the negative charges in the substance. If you try to increase the movement or the motion of metal atoms, you actually can do so pretty easily. Now, not to say that metals have low melting points. They have moderate melting points. It is kind of difficult to heat up and to melt metals. But that's not the only way, that's not the only form of motion. Motion can also be vibration. It doesn't have to necessarily mean lateral motion like sliding past one another. It can mean vibration as well. And if you look at the metal ions here, there's nothing keeping it directly in that position, right? It's got some room to wiggle, okay? So does this one, right? And so does this one. So the vibrational capacity of motion, or the capacity of vibrational motion for a metal is actually pretty high. So metals, as you can see over here, have pretty low melting points. Not melting points. They have pretty low heat capacities. Okay, we go from lead, which has the lowest one of all, 0.129, lowest one out of this list, I mean, up to cadmium, iron, and then all the way to aluminum, 0.897. Okay, so it would be correct to say that if you have equal mass of each of these, let's say 1 gram of each, it would cost you the least amount of energy to heat up lead. It would cost you the most energy to heat up aluminum. Okay? So, given that fact, let's read the question and see if we can answer this real quickly. Okay, if equal masses were used, which metal can absorb the most heat before the temperature would increase by 1 degree Celsius? Justify your answer. Which metal can absorb the most heat before the temperature would increase by 1 degree Celsius? That's going to be the one that has the highest heat capacity. It's going to be the one that's the most resistant to temperature change. So that would be aluminum. Okay, that's my claim. Aluminum would be the most, would be able to absorb the most heat before the temperature increased by 1 degree C. My evidence would be that the heat capacity for aluminum is greater than the others. Okay? And my reasoning would be just essentially saying what we've already said in the form of a sentence. So what could I say? Aluminum could absorb the most heat for increasing temp by 1 degree C. That's good enough, okay? All right, so that's the concept of heat capacity. Now, what are we using that for? Well, heat capacity is a value that is specific for different substances, okay? So liquid water has a heat capacity. Solid water has a slightly different, actually it's about half the heat capacity of liquid water. Metals are generally lower. Ionic solids are generally pretty high. Different common substances, you can look these values up, okay? These are sort of known values that scientists have investigated. You can use heat capacity in some different equations, okay? Namely, the heat transfer equation. This is called sometimes the MCAT equation because of the MC delta T, the delta being like the letter A, so the MCAT equation. This allows you to work with all the different variables that are inside of heat capacity, and it allows you to sort of analyze numerically the energetics of a situation from like the heat perspective. Okay, let's go ahead and jump into an example. Okay, I think that's going to help us the most. All right, so let's look at example number 1. This is number 57 on page 250B. So this is from chapter, I believe, chapter 5. We've got a 5-gram sample of one of these substances from table 6.1. So we've got liquid water, solid water, aluminum metal, iron metal, liquid mercury metal, and solid carbon. So we've got a 5-gram sample of one of these substances, and it says it was heated from 25.2 degrees Celsius to 55.1 degrees Celsius, requiring 131 joules to do so. Which substance was it? Okay. So let's take a look at this equation again. Okay. If we know the heat that was used, we know the mass of the substance, and we know the temperature change, then we can solve for that missing variable, which is the heat capacity. Okay. So let's take a look. Do we know those things? I think we do. So the formula, right, is Q is equal to mc delta T. You know, this is supposed to be easier for me here, and yet I'm being sloppy. Let me try this again. Okay, Q is equal to mc delta T. Okay, nice. Q is the heat, or the joules, the energy that was used. That's 131 joules. M is the mass, 5 grams. If we can solve for the heat capacity, then we can compare the value that we get to the value over here in this table, and that should tell us which of these substances this is. So we're going to be solving for C. Delta T is the change in temperature. So we're going from 25.2 to 55.1. I believe, well, we can type it in like this. 55.1 minus 25.2, and that's degrees Celsius. I think that's 29.9. Okay, so I'm not going to go through all of the algebra here. We're just solving for C. Let me get out my calculator real quick, and I will do this pretty quickly here. So we've got 131 divided by 5, and also divided by that temperature change. Okay, the value that I'm getting for C with 3 significant figures, since I've got 3 sig figs in my problem here, is 0.876. And if you look at the units, this is joules per gram degrees Celsius. We're dividing by those on the other side, right? So 0.876 joules per gram degree Celsius. And if I take a look over here at my values, that is most close to aluminum. Okay, so it's not exact, and these are experimental values, these temperatures and the mass reading, right, and the joules. So it's okay that these aren't exactly right on the value that's in the table, but it's pretty darn close. So we've got a pretty decent amount of confidence here that this substance was aluminum. Okay. All right. Let's look at the next example. All right. The specific heat capacity of a substance has units of joules per gram degree Celsius. So a little bit of vocab for you guys. There is a specific heat capacity and a molar heat capacity. These are both heat capacities, so it's the same concept. It's just whether or not we're talking about grams or moles. So are we talking about heating up 1 gram of the substance, or are we talking about heating up 1 mole of the substance? If you're talking about grams, use the specific heat capacity. If you're talking about moles, use the molar heat capacity. We are, in this problem, supposed to convert from the specific heat capacity to the molar heat capacity. Right? We're talking about aluminum again, our winner from the last problem. It has a specific heat capacity of 0.89 joules per gram degree Celsius, and we're asked to calculate the molar heat capacity. So this is as simple as converting from grams to moles. We're going to use the molar mass, or the atomic mass of this element, aluminum, to do that. You just have to pay attention to where the units are. Okay? So take a look at the value of the heat capacity here. 0.89 joules per gram degree Celsius. If I multiply by grams over moles, that's going to cause grams to cancel. And I'm talking about aluminum here, okay? So this value here, grams per mole for aluminum, I believe is about 27. I don't have my periodic table in front. Actually, I do. 26.98. Sorry, it was right over there on my desk. 26.98 grams per 1 mole. This is going to convert my specific heat capacity into the molar heat capacity. It really is as simple as that. So 0.89 times 26.98, 24 point, oh, well, I've only got 2 sig figs here, so I'm going to keep it at that, 24 joules per mole degree Celsius. Okay, so if you're asked to work with a molar heat capacity versus a specific heat capacity, it's fine. You can convert back and forth between the two of them using the atomic mass or the molar mass of that substance. Okay? All right, let's look at the next example. This is going to be the final one that I do on these. Actually, we'll see. We'll see how it goes, and then I might have to do one more. Okay, we've got a 25-gram piece of metal at 100 degrees Celsius. So this is 25 grams. It's at 100 degrees Celsius, and it is submerged in 100 grams of water at 25 degrees Celsius. Okay, so 25 grams at 100 Celsius, 100 grams at 25 Celsius. Putting the metal in the water. Now, what we can assume is that the temperatures of these things are going to meet somewhere in the middle. Okay, the metal is going to cool down, the water is going to heat up. Okay, however, they're not necessarily going to meet right in between 100 and 25. It depends on the heat capacities of the substances. Remember what heat capacity is, right? It's the capacity of a substance to resist temperature change. So the metal has a much lower heat capacity than water, meaning that the water is going to resist temperature change a lot better than the metal. So what we can expect, right? We've got something that's 100 degrees Celsius and something that's 25 degrees Celsius. We can expect the final temperature to be a little bit closer to 25 degrees C, okay? Because the water, which is starting at 25 C, is going to resist temperature change a lot better than the metal, okay? So we can expect the equilibrium temperature, to be a lot closer to 25 C than to 100 C. Now, how do you actually solve this problem? Well, what we've got to do is we've got to use that MCAT equation, okay? And actually, if you look over here off to the side, this is an important concept, okay? What this is saying is that the heat lost by the metal is going to be the exact same value or magnitude of the value of the heat gained by the water, okay? Heat is going to be going from the metal into the water, right? Because the metal is starting out hot, the water is starting out cold. They're going to meet somewhere in the middle. The heat is transferring from the metal to the water. So the heat lost by the metal is going to be equal to the heat gained by the water. That is what that is saying, okay? Now, don't worry so much about this negative sign. I'm going to mention that in the problem here once I get writing. But that's where we're going to start, okay, with this fundamental understanding that the heat lost by the metal is going to be the same as the heat gained by the water. Now, this is our overall equation, right? Q is equal to mc delta T. This, for the metal, is going to be equal to the same thing for the water, okay? So I'm going to start with mc delta T for the metal on one side and mc delta T for the water on the other, okay? So we're doing metal on the left and water on the right, okay? So let's start plugging in some values, things that we know. The mass of the metal is 25 grams. The heat capacity of the metal is 0.515. I'm going to start omitting units, okay? So I should be more careful about the units, but just for the sake of having this go a little bit quicker, I'm going to skip on the units here. The delta T, or the temperature change, this is an interesting one, okay? I know that the initial temperature is 100, and I know it's going to go down, but I don't know what that final temperature is. In fact, this is what I'm being asked in the problem. Calculate the temperature of the system once thermal equilibrium has been reached. So I'm going to use that variable x to represent the thermal equilibrium temperature, okay? This is going to be equal to mc delta T for the water. Mass of the water is 100 grams. Heat capacity of the water is 4.18 joules per gram degree Celsius. And the delta T for the water, here's where you have to be careful, okay? This is where the sign, negative, positive, this is where this can come into play. Ultimately, I want to have a positive value here equaling a positive value here, okay? So this temperature, this delta T right here on the metal side, that's going to be positive. It's going to be 100 minus x, which is going to be a positive value. I want to write my delta T on the water side. I want to write it so that it is a positive value, okay? I know that the water is going to heat up. It started at 25, it's going to go up to x, whatever that thermal equilibrium temperature is. X is bigger than 25. So I'm going to write it like this, x minus 25. That's going to ensure that this is a positive value, okay? So I'm going to have a positive entity on the left, a positive entity on the right, and this is going to work, okay? I've got a big long equation here, but I've got x here. Oops. Oh, goodness. What is happening? I don't know how I'm doing that. I've got x here. I've got x here. I just need to solve for x, okay? Now, in class, we looked at how you can use your calculator to do all of the algebra for you. Unfortunately, I don't have a nice little graphing calculator with me at this time. What do you guys think? You think it would be nice to maybe check this out on Desmos? I think it might be. Let's X this out. Let's go to Desmos, and let's see if we can figure it out on Desmos. Okay. How do you can you solve equations for x on Desmos? I think you can. Let me just type this in. So we had 25 times 0.515 times 100 minus x, and that was equal to 100 times 4.18 times x minus 25. Okay. let's see. I want to solve for x here. What do I do? You guys can tell I am not a big Desmos person. How do I get this to solve for x? Solve. Oh boy. Well, it's kind of a shame because in in class we learned how to basically type something in like this into the yellow calculators, and it will actually solve for x for you. You don't have to go through and do all of the algebra here. I am really unfamiliar with how to use Desmos. You guys probably know how to do this, and I don't. Functions here. Can you do... Where is the algebra? I just want algebra. Okay. Anyways, let me go back to the problem here. It ends up being very close to like 27 degrees. Okay, so solving all that algebra out for x, the thermal equilibrium temperature ends up being about 27, somewhere in that ballpark. Okay, and that's what we expected, right? We expected the metal to cool down a lot because it's got a low heat capacity, and we expected the water to resist that temperature change much better. It did heat up, but not by much, only up to about 27. Okay? All right. I think that that's good enough. I think those three examples allow you to work through the problems from 6.4. If not, obviously you can come see me, but I'm sure this video has already been quite long, so I'm going to leave it at that. Thanks for watching.